Hello Math 3680 students, welcome back. We just had the midterm exam in week 8. Now let's go to the second half of the course. The second half of the course content begins from the theory of estimation. This topic corresponds to Chapter 6 and Chapter 7 of our textbook. Chapter 6, point estimation, is relatively short and minor, and we're going to spend only one section in this notebook. And that one section, section 1, is de-emphasized in gray. The rest of this class notebook is all about Chapter 7, interval estimation. And that's a major section that we'll have to spend more than 1 week. Okay, let's begin Chapter 6, point estimation. And here is a definition according to our textbook. A point estimate of a parameter theta is a single number that can be regarded as a sensible value for theta. It is obtained by selecting suitable statistic and computing its value from the given sample data. The selected statistic is called a point estimator of theta. Alright, here we go, but do you understand what this is? I don't know about you, but it doesn't make a lot of sense to me. It's too vague. What do you mean by sensible value? Suitable, and how do you compute those values? Too vague. Let me try to be a little bit more explicit through a couple of examples. Example number 1. If you want to estimate population mean, what's the best point estimator? It's a sample mean, of course. Add up all the sample statistics and then divide by n the sample size. That's how you get the sample mean, and that is the best point estimator. Now, what if you're interested in the population variance and standard deviation? Of course, we look at the sample variance and sample standard deviation. That's not all. For example, if you're interested in the 70th percentile of the population, what do you look at? Of course, the 70th percentile of the sample, provided that you have sufficient sample size so that 70th percentile actually makes sense. Did I just say sufficient sample size? Yes, indeed. For small sample size, these kind of estimation will not be very good. For large sample size, they're going to be okay. And that's basically what the law of large numbers are talking about. But how do you quantify that? For that purpose, let's discuss these two concepts. Number 1, independent and identically distributed, IID. And number 2, simple random sample. The random variables x1, x2, x3, and so on are said to be independent and identically distributed if they are all independent from one another and they all follow the same probability distribution, independent and identically distributed. For example, if you have an urn of some colored balls, and then if you select a ball with replacement, put it back independently and repeat it, say 500 times. There you go. You have a collection of independent and identically distributed random variables x1 through x500 if you repeat it 500 times. If you repeat it 100 times, then x1 through x100. And that's because you're doing it with replacement. Without replacement, and they're not independent and not identical, and of course, you're going to run out of balls pretty soon. Now, any collection of independent and identically distributed random variables is called a simple random sample. In our textbook, in section 6.3, our textbook author explains simple random sample like this, but he doesn't really talk about independent and identically distributed. Maybe he did in some other section, some other chapter, but not in chapter 6. Nonetheless, I'd like to emphasize IID because it's going to be necessary if you need to look it up in some other textbook or internet or things like those. This is an important concept actually. A little bit advanced, yeah, but nonetheless, it's important. Independent and identically distributed family of random variables follow these properties. Property number 1. Expected value of sum is the same as sum of the expected values, the first equality here, and that's due to independence. You can prove it using multiple integrals and multiple summations, but that's a bit too deep, and we are not going to use multivariable calculus as a prereq for this course, so I skipped chapter 5 of the textbook, but the detail can be found in chapter 5. Now, these are not just independent, but also identically distributed. So all this expected value, ex1, ex2, all the way over to exn, they're all the same. They're all the same mu, so we have n times mu. Now from here, divide by n, then we get this. So x bar is the mean, so sum of all these divided by n, but this 1 over n can get out of this expected value, and that's general property. And here, expected value of this sum is the same as the sum of the expected value, and that's coming from the independence. And then these are all identical, so n times mu. So in the end, we get mu. Now, how about variance? Variance of the sum is the same as sum of the variances. And they're all the same, so n times sigma squared. Now from here, divide by n. What do we have? Sum divided by n, so that's my mean, x bar. And then 1 over n comes out as 1 over n squared, and that's true for all variance, because how do you define variance? Deviation squared, x1 minus mu squared, x2 minus mu squared, and so on and so forth. We have all the squares, and that's why we have 1 over n squared there. Now, variance of sum is sum of the variances, and these are all the same. So in the end, we have n times sigma squared divided by n squared, which was there before, so we have sigma squared over n. And then from here, if you take square root of this, then standard deviation of this x bar is nothing more than the square root of this, so you get sigma over square root of n. And this quantity is often called standard error of the simple random sample of size n. This quantity is going to be important, and we are going to be using it a lot in section 2 and section 3 of this notebook, and many more actually. But for now, let's leave it at that. And that concludes section 1 of this notebook, at least all the essential parts. Now, in a separate video, I'm going to talk about some theoretical background beneath this estimation, and then also this estimation, which are called law of large numbers. Actually, this one is called the law of large numbers, and this one is actually an application of it, some further manipulation. This one is called the law of large numbers. Okay, so much for this video, and we're going to talk about a little bit more theory in a separate video, a separate optional video. Otherwise, you can move on to the third video, which will discuss section 2 of this notebook.